Hello everybody. In this video, we're going to learn exponential random variable. This is part 1 of the series. On part 1, we're going to learn PDF, the probability density function, fx of little x. We're going to learn CDF, cumulative distribution function, capital Fx of x. We're going to derive the expectation of x, and we're going to derive the variance of x. Exponential random variable used to model many real-world events. It models the time that we have to wait until the success happens. For example, until the customer enters into your shop, success until the phone call you receive, time until a machine breaks down, time until a planet passes through some orbit. So basically it models the time that we have to wait until the success happens. Probability density function of exponential random variable is by definition lambda e to the negative lambda t if t is greater than 0 and 0 elsewhere. And the notation of exponential random variable is x exponential some parameters of lambda. And here you can see sometimes p or a, some different letters. I would like to use lambda for this video. So now we know the probability density function of exponential random variable. And the graph looks like this. The top point of the graph is the lambda, some constant number, some decaying exponential function, and 0 elsewhere. So this is our fx of t. Now we can derive the cumulative distribution function, capital Fx of x. So now we can derive the cumulative distribution function. Cumulative distribution function, capital Fx of t, by definition is the probability that capital X takes the value less than or equal to t. That means we are going to integrate the probability density function from negative infinity up to t. Here up to 0, since we have no contribution for the area under the curve, we are going to start from 0 to t for exponential random variable specifically. So fx of t dt by definition. We know that our probability density function fx of t is lambda e to the negative lambda t dt. And we know that antiderivative of, let's say, e to the at dt is 1 over a e to the at. So in this case, it's going to be 1 over negative lambda times lambda e to the negative lambda t plus c. Since this is definite integral, we're going to use fundamental theorems of calculus. So our antiderivative is lambda cancels lambda, negative e to the negative lambda t from 0 to t. Now our upper boundary is t, which is going to be negative lambda t minus e to the negative lambda times 0. So this is negative e to the lambda t, negative will be plus, e to the 0 is 1. So if you reorganize this, it's going to be 1 minus e to the negative lambda t. And if you use the variable x, you can say 1 minus e to the lambda x. So this is our cumulative distribution function from 0 to infinity. So let's make up fx of x 1 minus e to the negative lambda we use t, so let me change it to t if t is greater than 0, and 0 if t is less than 0. And the graph will look like this. So our top point of the graph is 1, and it is 0 up to t, and after t it's going to be asymptotic to 1. It's going to look like this. So now we know the probability density function. We derive the cumulative distribution function. Let's also see how we're going to use cumulative distribution function to compute any probability. So what does 1 minus e to the negative lambda t means? That means if we have probability that x is less than or equal to little x, or t in this scenario, in this picture, that means that we can use the function 1 minus e to the negative lambda x. And if your lambda parameter is like such value, let's say your lambda parameter is, let's say, 0.2, then you plug in 0.2 into your lambda and find the probability that x is less than or equal to x. We're going to see that in the examples on part 2 of this video series. Now let's derive the expectation. Expectation of any continuous random variable by definition is from negative infinity to positive infinity, x times the density function little fx of x dx. So we're going to apply this definition, and we can start our integral from 0 to infinity, because up to 0 we have no contribution to the area under the curve for exponential random variable. If you check the probability density function, as you can see here, there is no contribution up to 0. And we're going to multiply x times lambda e to the negative lambda x dx. This is integration by parts. You can use various methods to solve this integral. I'm going to use two different methods. One will be integration by parts formula, which is u times v minus integral of v du. And the second method I'm going to use is the tabular method. So let's start with u times v minus integral of v du. So you need to define what the u is and what the dv is. Our u here will be x. So our du will be the derivative of x, which is 1 times dx. Our dv is lambda e to the negative lambda x. And our v will be the antiderivative of dv. Antiderivative of that will be negative 1 over lambda times lambda e to the negative lambda x. Here lambdas cancel each other, and then we end up with negative e to the negative lambda x. Now we're going to plug everything into formula u times v, which is x times negative e to the negative lambda x minus integral of v, which is, we can pull this negative sign to the front, negative e to the lambda x, v times du. Our du is dx. And we end up with negative x e to the negative lambda x plus antiderivative of this, negative 1 over lambda times e to the negative lambda x from 0 to infinity, everything. Now we're going to apply the fundamental theorem of calculus. Now we need to plug in upper boundary and lower boundary for both functions here. So if we plug in infinity as our upper boundary here, infinity, negative infinity times e to the negative lambda times infinity, e to the negative infinity is 0. This is e to the x, and as you go to infinity, you approach the 0. So if we plug in upper boundary here, we obtain 0. Minus lower boundary again here, so 0 times anything will be 0, so 0 minus 0 from the first function, plus from the second we have negative 1 over lambda times, if we plug in here negative infinity, we're going to obtain negative lambda times infinity, which is going to be e to the negative infinity, which is going to be 0. We have minus by the fundamental theorem of the calculus, and if we plug in here 0, we obtain e to the 0 is 1, and we have negative 1 over lambda outside. So here we obtain negative 1 over lambda times negative 1 will be 1 over lambda. So 1 over lambda is our expected value of x. So this is our mu. Mu is 1 over lambda. Lambda equals to 1 over mu, vice versa. Alright, so now we have 1 over lambda as our expected value. The variance by definition is expectation of x squared minus expectation of x, the quantity squared. We already found expectation of x in the previous step, which was 1 over lambda, and we're going to square this quantity. And expectation of x squared can be found by the same method we found expectation, but this time we're going to multiply it by x squared. So from 0 to infinity, by definition, x squared times the density function, which is lambda times e to the negative lambda x dx. And this is a little bit tedious integration by parts method twice. So you're going to do integration by part twice. I did it here on my paper, and you obtain 2 over lambda squared. If you have any questions about how to do integration by part twice, please write on the comments. And if we plug in here the values, 2 over lambda squared and 2 over lambda squared minus 1 over lambda squared will be 1 over lambda squared. So this is the variance of exponential random variable. That's all for part 1. Before I forget, I would like to do tabular method that I promised. Our tabular method will be, let me do tabular method in the bottom here. So we were going to integrate x lambda e to the negative lambda x dx. So in our tabular method, we need to pick up u and dv. Our u is x, our dv is lambda e to the negative lambda x. And our derivative of u is 1, and antiderivative of this will be 1 over lambda, negative 1 over lambda times lambda e to the negative lambda x. Here lambdas cancel out and we end up with negative e to the negative lambda x. And here all we have to do is just to cross. and plus minus sign. Since there is nothing to multiply with 1, we have to go one more. Derivative of 1 is 0, and again antiderivative of this will be negative 1 over lambda, negative 1 over lambda times e to the negative lambda x, which is going to be plus. And we're going to obtain x times, if you multiply x times this, you're going to obtain negative x e to the negative lambda x, and we have negative sign here, minus 1 over lambda e to the negative lambda x, and you're going to plug in upper and lower boundaries as we did in the integral here previously. So you're going to obtain exactly the same values here. 0 minus 0 plus negative 1 over lambda times 0 minus 1, and you're going to end up with 1 over lambda. That's it for part 1. In part 2, we're going to do real examples. Thank you for watching.